take Analog with Wentworth. I'm pretty mad.
Yeah, you do.
Receiver's acting up a little bit, so we're just going to use the mic back today.
Sci-fi book. I mean, we know that the book's always about a movie.
It is. Trying to figure out why it's so crowded in here this morning.
Probably because you just gave a test that's always going to boost attendance for a while.
Usually nobody shows up the day after a test. All right, let's go ahead and get started. Our focus today is a new topic. It's a new way of doing design, or different from what we've been doing. In this course, we study basically two methods of control system design. One is using the frequency response, and today we're going to look at the time response of systems, and we're going to relate basically the time response to this idea of something called the root locus. So today what I want to do is introduce the root locus, and so let me first sketch a control system. Let me sketch the control system below here. So that's the simplest control system we can have here. And what we have is that we know the process model. Okay, we know the process model. And we're adjusting K. And for us, K is some number, some positive number between 0 to infinity. Okay. And so the question we want to ask ourselves is, how does the system behave okay. I want to emphasize that when I say we know the process model, that means we just know this box. We typically call this, we know the open loop. We call this the open loop. Okay. If we had some other boxes in the system, say we had something here or here, we would say that we would know all those things also. We call that the open loop. Okay? So the question is, how does the control system behave? And the control system is a closed loop question. The question is, how does it behave in closed loop? Now, what we could do is we could calculate the closed loop model. This is the output, and this is the reference. And the question is, how does the control system behave? And we'd like to get a fairly accurate answer to that question without calculating y over r, okay, or a closed loop model. Okay, this is what the root locus technique allows us to do. It allows us to answer this question of how does this control system behave? How does this closed loop system behave, given that I know just information about the open loop? You say, why do I know information about the open loop? Because it's a complicated problem, and we're working on with a team of people, and this is my responsibility to design this, and somebody else has designed the sensor, somebody else designed some signal conditioning. And we all know our individual parts, and we can get together in a room and say, well, this is the model for this part, this is the model for this part. Somebody else has designed an amplifier to do this. And the question is, when we put it all together, how will it behave? And certainly we could go through and calculate this transfer function from any input to any output, but we like to do that without having to do the calculation. And because the calculation requires time, because this is a complicated project, we may have to go adjust some things, and we may be iterating this over and over again. And in particular, what we're interested in doing is, as I adjust this parameter, as I adjust one parameter, what is going to be the closed loop behavior. Let's go ahead and calculate this thing one time today. Let's calculate this thing one time and take a look and see what we get. Okay, so let's calculate y over r. It's going to be g over, kg 1 plus kg of s, like so. Okay. And we know that we can focus on this part, the denominator. The roots of this thing are called the poles. We call it the system poles. Okay, just a review. And we know, for example, the issue of stability, we don't want to have any poles in the right half plane. No poles with real part greater than 0. That would be bad. That would be unstable. We also know that a lot of the time response the characteristic of the response is determined by the poles. The basic character of the time response is dictated by the poles. Okay. The zeros do affect the response. Don't get me wrong. They do affect the response. We're not ignoring the numerator. But the basic character of the response, whether it blows up or whether it decays, is dictated by the poles. And that's why we have this conclusion that we should have no poles with a real part greater than 0. So our focus is really this equation, 1 plus kg of s equal to 0. Okay. Okay. This is called the closed loop characteristic equation. Okay, when we were taking diffie-q's, when we look at a differential equation, we heard a thing called a characteristic polynomial. It's the same thing. Okay, but this is now expressed in transform domain. The closed loop characteristic equation. It's this thing that we want to avoid calculating over and over time. Every time I make an adjustment, k, I don't want to have to recalculate this thing. So k is a number that's going to, in our analysis in this class, for the most part, is a positive number between 0 and infinity. Okay, this morning what we'd like to do is we're going to take a look at an example, and we're going to go ahead and do this one time. We're going to go ahead today in class, will be the last time we do this, is to go ahead and calculate the closed loop poles by calculating the roots of this equation. The root locus technique, let me explain what is the root locus technique. It basically plots the roots of 1 plus k g of s equal to 0. It plots the roots of that. It plots the poles given information about the open loop. Okay. So remember when we did frequency response design, we talked about things like phase margin, gain margins, the stability margins. These are characteristics of control systems. But how did we do it? We plotted the open loop characteristic. And so from open loop characteristic, we got an idea how the closed loop system was going to behave. The root locus technique is similar. We know information about the open loop, we're going to get information about the closed loop. Okay? So the idea, the theme continues. Open loop information yields information about control system behavior. Okay, so we're going to start with this, and we're going to end up knowing what the roots are for the closed loop system. So this is the that's the root locus technique. It's a graphical technique. Okay, again, just like the frequency response a lot of time was done graphically, this is a graphical method. It's a graphical tool. Okay, because it plots something. Now today we're going to plot the root locus, but we're not going to use the tools. We're going to learn that when we come back Wednesday and Friday and so forth. Today we're going to go and do the brute force long way. The long way means we're going to go ahead and calculate this for one example. All right, so here's our system we're going to study. This is our example. We're going to do it the long way. Everybody needs to pull out a calculator. Let me see how many rows I got. 1, 2, 3, 1, 2, 3. We got 6 rows. The long way. We're going to draw this system, this model. Okay, we're going to control the position of a motor. Okay, and so the compensator, the controller, calculates a voltage, V, and this is the motor. When you apply voltage to the motor starts speeding up. And so this is the speed of the motor right here. Okay, I modeled as a simple first order model. Okay, we say we apply a step input right here, then the speed here increases something like this. But we want to control the position of the motor. And so the model is we integrate speed to get position. And so we're going to compare the actual position. This is the actual position to the desired position. Like so. If the positions don't match, if I have an error here, then I apply a voltage to the motor to get it to turn. If the positions do match and I have no error, then I say no voltage and the motor should stop turning. So I think heuristically we would argue this ought to work. Now the question we want to know is, will it work? Is this a stable idea? So we want to analyze this system. So what do we know is we know this model. This is what we're going to call G of S right here. This is the open loop, 2 blocks, okay? So G of S is 1 over S plus 2. We're going to do it the long way today. We're going to calculate the relationship between input and output. And let's calculate this thing. And so let's call this Y and call this R. Y over R is going to be K times G over 1 plus KG. So we have K over S plus 2. On the bottom, I have 1 minus K over S plus 2. But the loop gain has a minus sign, so that minus sign cancels out this minus sign, turns it into a plus sign. And then I multiply top and bottom by S plus 2. And I get K over S squared plus 2S plus K. And we're going to focus our attention on this, the closed loop characteristic polynomial. We want to find the roots of that. Notice that K is a number that we're going to adjust. Okay, and this is where our calculator work is going to come in. So what are the poles? What are the control system poles. They are the roots of s squared plus 2s plus k equal to 0. So we need our calculator to go in and find the roots. Okay, I think it's a solver on a TI 89. Is that what we're up to? Need a solver. You need to set up your solver to deal with complex roots. They may be complex. Okay? And your calculator probably is not able to handle this because this is a symbol. And so we're going to do it the long way today. We're going to put in numbers. And so we've got a bunch of rows here. So we're going to set up a bunch like this, K, and then we're going to solve for the poles, the roots of this equation. So we're going to substitute a bunch of K's in here, and we're going to do this. One, two, three, four, five, six. Okay. 1, 2, 3, 4, 5, 6, and I'll do this one. So if you're in the first row, I'd like you to substitute 0.1 into here and find me the poles. Second row, please find me the poles when k is equal to 0.2. Third row, find me the poles when the k is at 0.5. Fourth row, we'll do 1, and then we'll do 2. And the last row, find me the roots when they're equal to 5. And I'll substitute 0 in here because I can do that one in my head. So the poles are 0 and minus 2. Okay, shout it out when you get a number.
Negative 0.051.
Wait, negative,
0.051.
okay,
And negative 1.948.
okay, round them off to 2 decimals.
Can I give you more?
No. We gotta make that second row work a little bit. That's gibberish to me. I don't know what that is. Anybody else got a number?
Yeah, for 0.5, it's negative 1.71.
Negative.
1.71.
What's the other one?
Negative 0.229.
Okay.
For 0.2, I got negative 1.89 and negative 0.11.
Negative 1 and negative 1.
If it helps out, you could probably generalize that to negative 1 plus or minus root 1 minus k for your poles.
Negative 1 plus j, negative 1 minus j.
It's negative 1 plus 2j and negative 1 minus 2j.
Someone up here mentioned something about a general solution. General solution. How do we get the general solution? Somebody has to sing the quadratic formula song.
I ain't doing it.
You were volunteering for everything else. Come
My
on.
calculator did. I
Oh, let's sing the quadratic formula song.
Seemed so enthusiastic about singing it last time.
Yeah. Oh, what is it?
Root 1 minus k.
The new quadratic formula. Root 1 minus
That'd be pretty great.
Negative 1 plus or minus.
Square root of b squared minus 1.
Accurate.
Did I do that right?
Yeah.
Okay. Okay, so you see how tedious it is. It took us a terrible amount of time to do this. Those people in the 4th and 5th row aren't helping me out too much today. Okay? Yeah, it's complicated because they're complex roots. And for a simple polynomial, you know, we might be able to have some songs, little ditties that we can sing to help us find the problem. But you can imagine that this is going to be a little bit tedious to do by hand. And so that's why it's helpful to have a computer do this. So let's get back to the lab. Let's meet back in the lab on Wednesday. Okay, the computer certainly can do this a lot faster. We can set up a matrix of K's and have it solve for it. We won't do that because what we're going to learn is we're going to learn graphical techniques which allow us to solve and draw the picture quickly. But today we don't know those techniques yet, so we're going to do it the long way. So let's go ahead and plot what these roots look like. We're going to create the root locus. We're doing this the long way. Okay, we want to plot these roots. And since they're, in general, they're going to be complex numbers, we need to plot it in a complex plane. So this is the real part, and this is the imaginary part. This is the S-plane that we're doing these plots in. Okay, so what I'm going to do is I'm going to indicate, first of all, the poles of the open loop. And so we have a pole here and here. I indicate those with X marks. So these are the poles of G of S, the open loop. Okay. If we had zeros, we would add those to the picture as well. And we'll look at that on Wednesday. But today we're just doing a simple example. The next thing what we're going to do is notice that the poles of G of S are also when k is equal to 0. Okay, let's go back to our picture of our control system. We're trying to control the position of the motor, and if k is equal to 0, that means no information is getting through, no matter what E is, nothing comes out, so this is an open loop. And so all that's left is just this, and so the system runs open loop with no control, no input. And so the roots are 0 and -2. 0 and -2. Now what we're going to do is we're going to step down through our table that we created, and we're going to plot for each, as k increases, we're going to plot all these numbers. Okay? So the next number is -0.05 and -1.95. It's roughly here and here. Okay? And then we'll do the next number, -0.11 and -1.8. See, this one's getting a little bit more negative. This one is getting a little bit less negative. So I'm up to about here and to here. I'm continue on. Unfortunately, I got these two reversed. But as k increases, this one's starting to get more and more negative. -0.29 and -1.71. -0.29 is about here. -1.71 is somewhere about there. And then when k is equal to 1, I got -1 and -1, so they're both right here. I'm going to plot them right here, -1 and -1. And so basically, as k is increasing, if we had more time to calculate these things, they're moving along this line. And then when k is equal to 1, they're both equal. And then let's take a look at some more numbers. We got 2 more rows to do. When k is equal to 2, I get negative 1 plus j and negative 1 minus j. Negative 1 plus j is about here, and negative 1 minus j is about there. That's for k equal to 1. And then as k further increases, I get negative 1 plus 2j and negative 1 minus 2j. So negative 1 plus 2j is up here, and negative 1 minus 2j is about here. And so if we had more time to calculate more points, we would say that we would discover that they're moving along lines like this. Okay. Now what I like to do is like to add a little bit of some arrows to indicate what is happening at which direction do we move as k increases. And so I add a little bit of arrows like this, okay? This is basically for k increasing from 0 to infinity. When k is equal to 0, I was right here. As k increased, the closed loop poles, which is these heavy black lines, were on these lines. And then as k further increased, they moved this way. Okay, so these heavy lines here, these are the closed loop roads. Okay? These are closed loop poles, the set of all closed loop roads. So these are called the root locus. We have two loci. We had one set of points that started here, started at negative 2. You look at our numbers. We had one set of points that started at negative 2, then followed this, came down here, and then down here, then here, and so forth. And you say that one set of roots went like this, and another set of roots maybe went like this. We don't know actually what happened when, one started here, went this way, and one started here and going this way. When they got together, they were both the same. After that, we don't know which one went this way and which one goes that way. Now the computer's going to calculate it for us. MATLAB will calculate these things for us, and they will draw actual colors. And so this, some people call it a branch. It looks like a branch of a tree. The textbooks will call these loci. Loci is the plural of locus. Okay, loci is the plural of locus. Locus is a set of points. It's not what John the Baptist ate in the wilderness. Okay, locus is a set of points. What points? What points? Roots. That's why it's called a root locus. Okay? So we have, in this example, we have two loci. And the loci, the locus, the branches, I call these branches. Branches is a more plain English to me than loci. The branches are the set of all possible closed loop roots. The X marks are the open loop poles. Okay? So once we have the loci, we can start answering questions about the time response of the system. Okay? Once we have this picture, we can start answering questions about the time response of the system. Okay. The root locus reveals the character of the time response. It reveals the time response characteristics. So one of the questions I can ask is this control system workable? Is the control system, first of all, if it's workable, it better be stable. Okay. Is the control system stable? Well, we answer that by asking the question, does it have poles in the right half plane? Does it have poles in the right half plane? We look at this picture and we say, where are the closed loop poles? The closed loop poles are on the heavy lines. I look at the heavy lines For any k greater than 0, our loci lies entirely in the left half plane. They're in the left half. So our answer to this question is, this system is stable for all k greater than 0. Okay, we can adjust our controller gain freely without any fear of destabilizing the system. Now, when we come into the lab on Wednesday, we're going to go through a number of examples, and we're going to generate pictures that look like this. And by looking at these pictures, we're going to be able to characterize the time response. We get an idea of what the response is going to look like. Today, we did it manually, laboriously, point by point, calculating for a few k their points, and then we connected the dots together. And we say, this is what the root locus looks like. The root locus is a picture of the closed loop poles, given that we have information about the open loop. So, is the control system stable? Okay, so let's see what happens. Now let's say okay, let's suppose we make k big. Why would we make k big? Well, there's a lot of reasons to make gain large. Maybe we want to reduce the error. Okay, to reduce the steady state error. Maybe we hope that because the gain is large, the system will respond more quickly. I'm going to put a question mark there. Will the system respond more quickly? Okay? This was a model of a motor position control. Motor position control. It could be maybe a crude model of you in bed, and this is your position, and this is your mom, and she wants you down in the kitchen to eat breakfast. So you should be in the kitchen, but you're still in bed. So depending on her parenting style, she may put a little bit more gain into the problem or less gain. Okay, a little bit more gain means maybe she yells a little bit more, or she says something like, if you're not down here in the next 5 seconds, I'm calling your dad. And that would be bad. Okay? Will you respond more quickly? Well, let's take a look at the root locus. Okay? If you take a look at the root locus, what we get is we discover that as k is large, the roots are complex. So, will the system respond more quickly? Roots are complex. Somebody generalized it and said it's -1 plus or minus j (4k minus 4 square root), something like that. Okay.
It should be 1 minus k, shouldn't it?
I'll put the j here. So. Okay, something like that. A real part and an imaginary part. All right. And we remember when we studied the time response, that means the response did this. It has a real part decay, e to the minus real part times t, and it also has a sinusoidal behavior governed by e to the minus j imaginary part times t. Remember Euler's identity? So the response is going to do this. It will always decay because the pole's in the left half plane. But we also remember that the time constant tau was 1 over the real part. And so our conclusion here our conclusion here is that k gets bigger, the roots become more imaginary. So in this particular case, as k increases, the imaginary part gets bigger. As k increases, roots become more imaginary, but the real part doesn't change. It's equal to -1. So the time constant, tau, is equal to 1/1, which is equal to 1. So the settling time is equal to about 4 tau, is equal to 4 time units. So the observation is that increasing k increases overshoot because things become more imaginary, but in this case does not reduce settling time. So, back to mom trying to get you down to breakfast. If she yells more, your behavior just becomes more erratic, but you don't get to the table any faster. Okay. So, we can get from a picture of the root locus some ideas of how the system responds, the time response is going to be. So the time response is related to where the poles are going to be. Okay, so here are two of the questions that we could answer. We could answer, is the system stable? And does the system respond more quickly? All right? Okay, so let me kind of summarize again what is the root locus technique. The root locus techniques is going to start off with information about the open loop. Given that we have the open loop model, what we're going to do is we're going to sketch the set of all closed loop poles. Okay. Sketch means we're going to draw a set of points. And so this is called the root locus. Okay. And then for the design technique, what we're going to do is we're going to basically adjust the picture to achieve desired time response. So somehow in our mind, we have this mapping that goes between time response, how quickly the system responds, and whether it overshoots or not. We have some sort of a picture of that in time, and we have somehow translated in our mind to locations in the S-plane. And so this is the skill that we learned here in this class, is how do we relate S-plane locations to time response. Okay, on Wednesday, we're going to go in and in MATLAB, we're going to sketch the root locus. MATLAB is going to sketch the root locus very quickly for us. What we're going to do in this class is we're going to learn how to sketch these things by hand. And we do it by hand not because that's the way we do things anymore. We do it again just like the Bode plot. We don't do it by hand anymore. We learn to do it by hand simply as a sanity check of what the computer is giving us. Okay, so in MATLAB, we are given in our mind this model. Okay, And so what we're going to do is we're going to say g is a transfer function. The numerator is 1 and the denominator is s squared plus 2s plus nothing. Okay, so this is what we should be writing in MATLAB. And then what we're going to just say is r locus of g. Okay, notice that we're using the open loop model. Okay, use open loop model. And this will draw the picture for us. Now, long term, what we're going to do is we're going to try to do a little bit better design. And so let me give you a preview of what's coming up. And we're going to basically do a control system design. And so what we're going to have is we still have this gain k that can be adjusted, but now we're going to add a compensator here. And here's our process. Here's the process. We're going to design this and adjust this. So we're going to initially start off with just this picture, the picture using only this because there is no compensator. But then what we're going to do is we're going to add a compensator, and so then the new open loop, this is what we call the compensated open loop. And so what we will do is we will do a root locus of C and G. Whatever C and G is, we need to calculate G, we need to calculate C, we need to figure out what the series combination is. We can do all this in MATLAB. But again, we're still using, it's still an open loop. It's still an open loop model. Okay. But we're going to change the picture because we're adding something here. The picture, the root locus, changes when C is added. Okay. All right, so on Wednesday, let's again go back to the lab. We're going to take a look at some of these things on the computer and run through some examples more quickly, and at the same time be introduced to some of the rules for how to sketch things by hand. Okay, let me talk a little bit about exam 3. As I was grading it, I realized I had mislabeled the exam. Your exam says exam 2 on it, but it actually was exam 3. Most people struggled with the first problem. They did pretty well with most of the exam, but the first problem people struggled with, and that was, let me speak just a little bit about that. Problem number one dealt with 0 dB bandwidth and also 3 dB bandwidth. Okay. 3 dB actually means negative 3 dB. Negative 3 dB means the gain is equal to 1 over square root 2, or square root 2 over 2, or 0.707. And so what you had to do in this problem is you had to calculate the gain manually. Okay, the model was k over s plus a squared, and this threw off a lot of people. Okay, a lot of people just said, well, the bandwidth is equal to a. Okay, that's only true if it's a first order system. Okay, that's only true for first order, but not true for this system. This is a second order system, so you have to calculate the gain. And you have to remember that we're dealing with frequency response, so we have to find the gain of k over j omega plus a quantity squared. and you have to figure out how do you calculate that gain. Okay, we're given omega. I'm told that the bandwidth is going to be n. N is the number of letters in your first name, so this is given. And then we have to calculate when this is reduced. Well, the nominal gain is when omega is equal to 0, the gain is k over a squared. So we have k over a squared, and we have to see when that is come down 1 over square root 2 over 2. So this is the equation that has to be set up and solved for a. Okay, and you see that k doesn't have any bearing on the problem, it cancels out on both sides. Now to calculate the 0 dB bandwidth, you got to go back in and you got to solve for this, and then what we want is we want to see when is k j omega plus a quantity squared, when is the magnitude of that equal to 1. So this is the other equation that I have to deal with. And now k does have a bearing on that problem, but you have to first find out what a is. Okay, I think 2 people in the class got this problem right. Okay, but most people just were lost in the weeds. They did pretty well overall on the rest of the test. We have a couple people who have not taken the test. One's going to take it this morning, and one's going to take it on Wednesday. So the solutions will be posted on Wednesday. But I'm going to go ahead and give you your exams today.